all hear me? No? Okay. Oh, okay, thank you. Okay, so maybe I would just take a quick attendance check. So let me find T. So, Okay, I think Junxi. Okay, because some of you are using your maybe phone number to show in the Zoom. So for the attendance, I think you will have to um take the attendance in the next class. Okay, is that okay? Okay, so let's begin. Let me just share my screen first. Oh, okay. Okay, so can you all see the screen that I'm showing? Yes, okay. So, so today we will be talking about um uh the advanced version of the visual language model. So we will discuss how the vision language models are actually being trained to understand chart data. Okay, and if we have some time at the end, I will take some questions or maybe some consultation as well. So I'll we will see how it goes. And please stop me if you have a question. Okay. So let me make this. Okay. So um okay, let's just start now. Okay. Okay, so welcome back. Today we aren't just going to look at another model release. We are going to look at a philosophical pivot in how we build vision language systems. If you have been following the AI space for the last few years, you have seen the explosion of chat models. So you upload an image to ChatGPT or Gemini, you ask what it is, and it chats with you. It is polite, it is conversational, and it is incredibly broad. It knows a little bit about everything. But what if you don't need a chat partner? What if you are building a system to read serial numbers of engine parts in a factory, or a system to detect tumors in X-ray, or a drone that needs to spot weeds in a field? So you don't need a model that says, here is a list of weeds I found. I hope it helps. You need a system that outputs the coordinates, so precision and speed. And you need to run it locally, not a massive server farm that will cost you $20 for a few million tokens. Now think about what happened when you try to use those big chat models in a real production system. So you send an image up to an API and you wait for, say, 200 or 800 milliseconds for a round trip. You pay per token, and your JSON parser crashes because the model returned 3 sentences of pleasantries wrapped around a single answer. And if your system goes offline or your customers have no internet connection, your data is too sensitive to leave the building, and your entire pipeline breaks. So this is the gap. So on one side, a powerful but bloated cloud assistant. On the other side, engineers who need something lean, low code, and precise. So this is what we're going to uh, discuss today, the Polygamma model and its successor Polygamma 2. So the original Polygamma is a 3 billion parameter model. Polygamma 2 extends this family upwards. So this family have, okay, this family have 3 billion, 10 billion, and 28 billion variants. But here is what it matters. The 28 billion model is not a chatbot either. Scaling up did not change the philosophy. The largest Polygamma variant still a very precise tool and still designed for fine-tuning, still structured around the same specialized task prefix. And Google scaled the capacity without abandoning the engineering first identity. So Polygamma is not a chatbot. It is a visual language transformer. It was never designed to be a chatbot. It is Google saying, like, here is our best architecture, stripped from the personality, stripped from the pleasantries, stripped of everything except the core capability. Now go to build something. Now I will let you to go build something with it. So it is not a product, it is sort of like a foundation, a precision instrument that waits to be wielded. This distinction matters more than you might think because when you understand what kind of things polygamma is, every design decision we are about to study, the choice of vision encoder, linear projector, and the base language model, the training stages snapped into focus. It all makes sense once you understand the goal. So in this first section, we are going to build that foundation. We will trace the evolution of a visual language system from clumsy pipeline of 2015 to the elegant unified transformer that we have today. We will trace the Pauli research lineage that proves scaling laws apply just as powerful to image as to text. And we will examine the 3 flavors of polygamma checkpoints that Google ships and understand which one you should reach for in any given situations. And we will close with some discussion about the economics and the number that explain why this family of models was built at the scale it was. So it is not just a model history, it is the reasoning behind every engineering choice that you will encounter in the following sections. So let's begin. Okay. So to understand why polygamma is built in the way it is, we have to look at the prehistory of our field. And it hasn't always been easy. So go back to 2015. The paper was a show and tell. It was the kind of, you can say, the stone age of image captioning. So back then, we treat vision and language as two completely different species. If you have been paying focus in semester 1, we talked about CNN and RNN and how we stitch them together. So on one side, we had convolutional neural networks, CNN or ResNet or Inception. These were great at classifying image. They could tell you this is a dog or this is a cat. On the other side, we had recurrent neural networks and LSTM. These were good at predicting the next word in a sequence. So how did we combine them? If you remember semester 1, we didn't really. We just glue them together. Like we would take an image, run it through the CNN, and take the very last feature vector, a single list of number, and shove them into the LSTM at its starting memory. So thinking about how limited that is, you are compressing the entire complex scene, say, for example, a park with a children playing and a dog chasing a frisbee and a cloudy sky into a single vector. If the convolutional neural network decided frisbee wasn't important enough to be in that vector, the language model had zero chance of actually talking about the other parts of the image, say, for example, frisbee. So the information was lost and the language model was kind of blind to the raw image. It only saw what the CNN summary allowed it to see. Okay. So then come to 2017, the Transformer paper changed the text forever, but it took a few years for vision to catch up. So by 2019, we started to see models like visual bird and LX MERD. So these models try to be smarter. They say, okay, so instead of a one vector coverage, let's treat the image as a set of regions. And they would use an object detector to find bounding boxes, and then let the text model attend to those boxes. So this was the era of cross tension. You had a text streamed it and an image streamed it. So and they will talk to each other at every layer. So we have talked about cross attention from the I think from this third week. Um, and you had the text stream and image streams, and they talk together saying, hi, I'm processing the word dog. Do you have any dog regions in your image streams? So it works better, but it was very heavy. So if you recall the computation complexity, it's because of the square matrix, you have at least n to the power of 2 size of the attention matrix. So it was slow, and it requires training distinct object detector first. And so fast forward to 2022 and 2023, we had a realization. The most powerful idea is that text was next token prediction, just predict the next word. And the question became, can we treat an image as a bunch of words? So if we chop the image into tiny square and patches and flatten them, aren't they just tokens? So we talked about this over the last two lectures. And so we just put them in one big transformer. Image tokens go in, image text tokens came out. And this is the generative era. So this is where the pipe polygamma sit. So the third era. So we have the second era cross attentions, and we have CNN plus LSTM. So the third era simplifies everything. So no special vision loss function, no bounding box retrain, just input image, input text, and predict output text. This is simplicity, and the simplicity is what allows it to be so versatile. Okay. So now polygamma didn't just appear out of nowhere. Okay. So it is a result of a very specific, very expensive research program in Google called PALI. The full name is actually Pathways, Language, and Image. Pathways, Language, and Image. So you need to know this lineage because it explains why polygamma is so efficient. So the first Pali model were gigantic. They were built to answer simple questions like do neural scaling laws apply to image? They were built to answer a fundamental questions asking whether the neural scaling laws apply to image, because we already know that text apply the neural scaling law apply to text. And we knew that if you make the text model bigger, like GPT-2 to GPT-3, it gets smarter. So does that happen if you make the vision part bigger? So Google trained PALI-X, this one, a 55 billion parameter model. And it has a massive 22 billion parameter vision transformer, which is very gigantic. If you remember the OCR that we talked about, the pedal OCR that we talked about is only like about a billion. So 22 billions is quite large, even uh, at that time. So um, they found that as you make the vision encoder bigger, the model gets better at fine-grained task. It stops just saying a table and starts saying a full complete sentence. For example, a coffee table with a scratch on the left leg. But there was a problem. 55 billion parameters is huge. You can't run that on your laptop, and you can't put that inside a robot. So then came the breakthrough of the paper, Pali Gamma 3. The researcher asked, say, can we get the performance of similar 10x larger models, but with a 5 billion parameter package? So they changed the recipe. So first they use SIGLib, which we will talk about, SIGLib. I think it's very similar to CLIP if introduced in the first semester. SIGLib is then for sigmoid. Okay, do you have a question? No? No? Okay. Okay. So SIGLib stands for sigmoid loss for language image pre-training. The visual encoder scaling it to 2 billion parameters, and Pali in Pali 3. So we will do a deep dive on this section in section 3, but the main point is it learns much better from noisy web data. Second, they realized that resolution actually matters more than the parameters for the document task. So a small model seeing a high resolution image reads text better than a giant model see a blurry image. So the original Polygamma is open sourced which is the child of Pali 3, while the Pali Gamma 2 builds on this with Gamma 2. The original Pali Gamma is inspired by Pali 3 architecture, combining a 400 million sigmoid SIGLib vision encoder with the 2 billion GAMI 2B GAMI language model. And the polygamy uses Gamma 2 model, which have 3 version 2B, 9B, and 27B for enhanced performance. So it inherits that smaller, faster, stronger DNA, and it punches way above its weight class because it uses these hyper optimized components like SIGLib rather than just raw scale. Okay, so let's talk about the philosophy of this model. It is the part that strips people up. If you go to Hugging Face and try to chat with the raw polygamma model, you might be disappointed. If you say, "Hi, how are you?" it might not respond. If you showed it a picture of a sunset and say, "Describe this," it might just output a short caption. So this is by design. There is a fundamental difference between a chat assistant and a base model for transfer. So think of GPT-4V or Lava as a Swiss Army knife. It is a knife, a screwdriver, and a pair of scissors and a toothpick. It can do a little bit of everything. And I think this is great for exploration, but if you are a carpenter, you don't use a Swiss Army knife to build a house. You use a dedicated saw. So you use a dedicated hammer. So polygamma is a block of high quality clay. So Google has pre-trained it on massive mixture of tasks like detection, segmentation, OCR, captioning, not to make it a chatbot, but to give it the clay potential. So by showing the models billions of documents during pre-training, they taught it the clay like how to read by showing it in millions of segmentation tasks. Um, it taught the clay what the object what objects looks like. This philosophy like trained broadly and allowed it to transfer deeply. So the goal is for you, the maker or the engineer, to take this clay and mold it into the specific tool that you need. So you do if you need to a license plate reader, you can take polygamma and show it, for example, 500 image of license plates, and you fine tune it because it already knows how to read and how to see objects from this broad training. It adapts instantly, and the results, the model has a better license plate reader than a generalized chatbot. And also it is smaller and faster. So this shifts the mindset of being the use of polygamma. You are actually building it with polygamma model. Okay. So okay. So practically, how does this manifest? When you go to download the model, you will see three flavors. So you need to pick the right one. The PT is called the pre-trained. It's the rawest form. It has seen images and text, but hasn't been taught specific tasks. Use this only if you have massive data set and you want to teach it something completely alien, like reading some earthquake detection readouts or something like this, or read heartbeat, the chart of a cardiomyogram, or read a EGG myogram. Okay. So mixed stands for mixture. It is the generalist starting point. It has been trained on a blend of tasks. It can detect, it can caption, and this is where you should start 90% of the time. You can take the mixed model that you fine tune it on your specific data. So fine tune, the FT stand for fine tuned. And these are academic proofs. So Google released a chart QA version and a science QA version. These models are kind of specialized. The chart QA model is a genius at charts, but might forgot what a doc is. So you use this only if your task matches the benchmark. Exactly. Okay. So for project, I will presume you'll be using the middle one. Okay. So um let me oh sorry. So let me close with the question that drives every architectural decision in this model family. Why 3 billion parameters, and why does polygammas offer two offers 3 billion, 10 billion, and 28 billion options rather than just one size? So the answer is not very academic. It's actually the VRAM limitation. So the physical economical constraints that governs where the machine learning model can actually live in the real world. So below 4 GB of VRAM, the micro tier, it is sort of like a Raspberry Pi territory. These are the tiny quantized model that can barely classify an image, let alone answer questions about it. Useful for weak word detection on a sensor, not for document understanding. 8 GB to 16 GB of VRAM is the customer tier. So this is for example, a gaming laptop or a free collab instance, a MacBook with, say, an M series chip. This is where hundreds of millions of devices live. So this is actually where Polygamous sits or position itself. And 24 GB to 80 GB VRAMs are for the professional tier. So for example, an RTX 4090 on a workstation, or an A800 in a data center rack. Okay, so imagine you are a founder building a smart architectural drone that flies over a field. Photographer crops that flags potential disease patches for a farmer. So you need a vision intelligent on board, because you cannot stream raw 4K videos over a rural 4G connection to a cloud API. So the latency alone will make the system unusable. And you kind of have two options. One is use a 70 billion parameter model running in a data center, but although it is powerful and accurate, it costs you $2 per thousand API calls. And there is a minimum 200 microseconds round trip, millisecond round trip latency. So, and it cannot be used at the moment that the drone flies outside the mobile coverage. And the second option is use polygamma. So just a 3 billion parameter model, maybe quantized to integer at 8, running it locally, consuming only, say, 10 watts per power, and can detect blight patches and outputs precision bounding boxes, coordinate, and does it in 15 frames per second. So no internet connection required, and no API builds, and no latency. So the 3 polygamma fits roughly to 6 to 8 gigabytes of VRAMs, and at a flow 16th precisions. And if you quantized it, it can drop below 4 gigabytes. So this is exactly where the polygamma fits. It was designed for this kind of scenarios. Okay, so let's take this back and ask what we have actually established in this section before moving on to the architecture section. So we have established why do we have polygamma in this size and why polygamma is not suitable for chat application. And why the architecture? Because for a decade of research coverage on a single insight, treat image as tokens and feed everything into one unified transformer and predict text. Generative simplicity beats complex pipelines every time. And why why the philosophy? Because engineering production system requires precision tools, but not conversational assistance. So Polygamma is not exactly a chatbot. So it's not exactly that you can pick up and run. So Polygamma is sort of like the clay and you are like the sculptor. So the best specialized and personalized tool always beats a generalized when the task is well defined. And also talking about the size, why 3B? Because it fits in many um, industrial cases, and it won't limit by the VRAM limitations. So it fitting inside the consumer's hardware is the first class design requirement. It's not an afterthought. And crucially, um, the generative architecture is what made it possible to achieve high accuracy at 3 billion parameters. The 3 billion target is what makes edge deployment viable. And the edge deployment viability is what makes the specialized tool philosophy worth pursuing at all. Okay. So now in the next section, we are going to talk about the actual architecture. Okay. So before we move on, any question? Okay. So we now look into the core architecture. So if you are an engineer coming from an old world of computer vision, you might expecting a fairly complex design of polygamma model. However, prepare to be surprised. The architecture of polygamma is radically and almost aggressively simple. It's just composed of exactly 3 pieces, and encoder, which you can think of it is the eye of the model, and a projector, you can think of it as a glue or a translator or a connector between the eye and the brain, and a decoder, the brain. So that's it. So it is like a Lego set. So Google took a pre-existing vision model off the shelf and took a pre-existing language model off the shelf and glued them together with a simple mathematical connector. So we are going to take a high-level tour of these 3 components. And I think we aren't going to bog down by the math of sigmoid loss function or the rotational positional encoding like in the last lecture embedding yet. Um, we have we would like to have a overview of the model. So the goal here is to understand how the data flow through the model. And we want to actually trace the journey of data getting in as a pixel and travel from the input of the model to the output, say a word at the end, for example, a cat. Okay. So this is the anatomy of polygamma. So from the input image, you have patched embeddings like we have talked about. Licks, thick lip. We briefly talked about it in the last uh, lecture, but we have not discussed the details of thick lip. And the linear projector, and of course the text tokenizer, concatenate them together, and then we are going to feed it into the uh, text generator, the gamma, the gamma brain, like output, so for it to output the text. It uses some techniques, say, for example, MQA that we will talk about, and finally output the text token. Okay, so the first component, let's start with the left side of the diagram, the vision encoder. It is the eye of the system. So polygamma uses a model called cyclic so 400 million, 400M. And you might be familiar with CLIP, contrastive language image pre-training that you have learned in the last semester from OpenAI actually. CLIP is the standard I for most multimodal models. Okay, so CLIP is Google's upgrade to CLIP. Okay, excuse me for a sec. So we will spend all section 3 explaining why it's better, but for now, here is what you need to know. It is just a simply vision transformer. It has about 400 million parameters. So overall cyclic model is 0.9B, and it doesn't see image the way a convolutional neural net does. It is a grid. Um, so specifically, it chops it into 14 by 14 pixel patches. So if your image is 224 pixel wide, you get 256 of these patches. If your image is 448 pixels wide, you get 1024 of these patches. So and so on. Each of these patches is flattened into a list of numbers, a vector, and the cyclic process them all at once. So its job is to look at a patch of, say, a dog ear and a patch of dog tail and understand and how they're related to each other visually. So by the time the data leaves this component, it's no longer uh, pixels. It is a sequence of visualized um, tokens. Okay, it is a sequence of visual tokens. So think of this word. Think of these as words in vision language model. One token might represent fur texture, and then other might represent curved shape. So the output component is a list of these vectors. Each vector has a specific sized 1,152 dimensions. Okay, and but now we have a problem. Our vision encoder cyclip speaks vision and outputs the vector of 1,152 numbers long, but our language model Gamma speaks the text. It supports vector expect to be 2,048 numbers long. You cannot just plug the two together, so it just won't fit. And this is where the component two comes in, the projector. So in many models like lava or flamingo, researchers get kind of creative in here. So they use heavy resamplers or multi-layer perceptions, which with activation function, and they try to do complex processing in the gap between vision and language. In contrast, Polygamma does the simplest possible thing. It just do the linear projection. So if you record what you have learned in semester one, you have been taught about how a neuron works. So neuron have input weight times the weight and add them together and output alongside with the activation function. In Polygamma, in the projector of Polygamma, it does not have the activation function. It's just a simple multiplication and adding. Okay. So no ReLU, no GLU, no hidden layers, no complex logic. The main job of component two is just to rescale the dimension. And Google research show that simpler is better. So this layer acts as a translator. Say it says, okay, cyclip, you have a vector presenting fur texture. I'm going to translate into the 2048 dimension vector that Gamma understand as a concept of softness. Because this layer is so simple, it forces the vision encoder and the language model to do the heavy lifting. It doesn't allow the glue to hide any complexity. So out of component two, we have a sequence of factors that are now 2048 dimension wide. They look exactly like text embeddings, but carry visual information. Okay. So now finally we arrived at the brain, the Gamma 2B. It is a standard text generation model. If you use GPT-2, Llama, or Mistral, you know this architecture. It is a decoder-only transformer. And Gamma usually expects text like the cat sat on and then it predicts the mat. But polygamma, in polygamma, we feed it say, for example, a cyborg sentence. The input sequence looks like the first 256 visual tokens are from the projector. Then the text prefix describes this image. So to gamma, those first 256 tokens just looks like a string foreign words, and it does not know they were originally pixels. It just sees 256 embedding vectors followed by English text. So its job is to apply a massive reasoning capability learned from reading 2 trillions of tokens of the internet to this mixed sequence. So it attends to the visual tokens. Say, oh, I see patterns of furs and years, and attends to the text token. The user wants a description. And then it does what all LMs do. It predicts the next token. Okay, so Gamma 2B is a 2 billion parameters model. It is small by modern standard, but it is dense. So it was trained on code, math, science papers, means that it brings logic to vision task. It doesn't just recognize a chart. It can read the number on the axis and performing subtractions because it learned math from textbook during its pre-training. Okay. So now let's put it all together. So let's trace the full life cycle of a single request. So imagine you are building a fruit counter. So say for example, you maybe some industry require you to count fruits, or maybe you want a sophisticated AI to assist you to counting fruits. So you have a picture of a bowl of apples, and you want to ask how many red apples. The first step is resize and patch the processing. So your 4K images from, say, your phone is way too big. Polygamma resized it to a fixed square. And let's say we used the standalone model, 224 times 224 pixels. It chopped this square into 256 little patches, 14 by 14 each. And step 2, the decoder. So these 256 patches rushed through the 27 layers of SIGLIB encoder. The encoder enriches them and a patch that was just red color. So talks to its neighbor and realized this is part of a sphere. So outputting the 256 vectors, each with 1,152 numbers long. So step 3 is the projector. So these 256 vectors hit the linear projector, and the matrix multiplication happens and reduce and the output sorry, not reduce, output the 256 vectors, each with 2,048 numbers long. So it increased the number size, the vector size. And then For step 4, now we prepare the text prompt, detect Apple, and we tokenized this text into say 3 tokens and glue them back together. So now we have 256 plus a 3 text token to form 259 tokens. Okay. So in step 5, the gamma 2B takes these 259 tokens. It used an architecture trick called prefix LM masking to look at the whole image and the whole questions at once. So, and then it will go through all the layers and generate output tokens, say Apple. And it output specialized location coordinates for the bounding boxes. In step 6, it decode. So we convert these location tokens back to the pixel numbers of X and Y coordinates and draw a box on your screen. So these are special tokens that it use. Okay, so before we close this section, we need to talk about the resolutions. So this is the single most important configuration choice you'll make for your project if you are going to use Polygamma for your project. And Polygamma comes in 3 sizes. The architecture changes slightly for each. So the 224 pixels model is the standard one. So the input is 250 visual tokens. It is fast, very fast. 256 tokens is nothing for a transformer. It use this for general object detection or captioning natural images. Okay. The 448 pixels model, it takes in the inputs is 448 times 448. Visual tokens length is 1024. So we doubled the resolution, which means 4 times the area. Now we now have 1024 visual tokens. This slows down the language model significantly, processing around K tokens and takes 4 times longer than the 256 in the attention mechanisms. I think use this for OCR if you need to read text. 224 pixels simply blurs the letter too much. 448 pixels is the minimum for reading. So in the last lecture, we have talked about the pedal OCR. In your project, you might be interested to compare the pedal OCR, the state of the art, to the Polygamma model of a specific OCR task. So you might try fine-tuning the pedal OCR and also fine-tune a Polygamma of this size and see which one performs better. And the 896 pixel model, the specialist, the input is 896 times 896, and the visual tokens is 4096. It is relatively heavy. Processing 4,000 tokens for every single image framed is computationally expensive. But document understanding, handling a full pages, say a A4 PDF contract, you might want to use this one. So the architecture is elastic. The cyclip encoder and the projector scratches to handle more tokens. So GAMI just sees a longer sequence, but remember the latency scales quadratically with the sequence length in attention layer. So move from 224 to 896 is not without a cost. And the kind of, I would say, the beauty of Polygamma is that you can choose. So we have, okay. So we have mapped the the encoder, the cyclip, and the translator, and the brain of the model, and we know how they are actually connected together, and we have introduced the data flow. Well, actually, this raises more questions than it answers. So why cyclip is better than the clip, and what is sigmoid loss? And why does the simple linear layer work? Doesn't that lose information? And why does gamma actually understand coordinates? And in the next three sections, we are going to we're going to talk about this, and we are going to open up component one, the cyclip. Cyclip is introduced in this week because it was planned to introduce in this week, not last week, but since the pedal OCR just came up, so it's kind of jump into the queue. So last week we talked about OCR as for the pedal OCR. Okay, but formally we have not formally introduced cyclip, and look at the math inside and kind of understand why it is so efficient. So before we move on, any questions? So I'll be here waiting for some questions, and I think we will take a short 20 minutes washroom break. If you have any questions, please feel free to ask in here. Okay. So long time. Okay, because we're using Zoom, let's say we come back at 10 to 4. Okay. So I'll give you a short break. And question Welcome. Okay. So any questions? Mm, okay, if no other questions, um, let's take a 15 minutes break. So because there are no questions, okay, okay. So see you in the next 15 minutes. Okay, so during the break, a student asked about the project. So if you go to the Moodle, hold on a second. There is a short guide on how the project should go. Um, okay, so essentially, the title of the course is deploying personal LLM or ELMs. Essentially, is um, we expect a to you've kind of picked a model and then think of an application that this model um, may be good for the case and try to either fit the model to um, for your task or to kind of you can fine tune or not fine tune the model, but you have to give your reason and deployed in the HPC server. So we have not talked about the deployment and setup in this course. I think um, once we talked about the deployment, it is, I think, fairly straightforward to deploy. We have, I think, 4 GPUs available for the presentation. So I think each group can deploy during 4 groups can deploy their model during their presentation. If not, please deploy the model and inference and take a screen captured. Then, and of course, you need to provide the deployment code so we know that you really actually deployed it, the personalized LLM, and the presentation and documentation. So the setting up of um, the model or the project includes fine-tuning that we have introduced in the lab. The most simple way to do or I would say the most, the expected way of doing the project is to go through a lab. So say in week 3, we have a lab. So you download the code, you understand the code, and because the lab itself will produce some results for you to report. Say, for example, week 5, hold on a sec. Week 5, let me extract all extracts. Okay, week 5. Okay, say for example, week 5, there are code examples telling you how to load the data set and do some inference of the data set. So in your project, I first want you to think about use cases that would fit. I've just made some examples, for example, fruit counting. So if I want to have a personalized AI agent for me to counting fruits, or if I want a personalized AI agent that can do a very specific task, because for such a low size or such a small size model, I do not expect you to build um, a very genius chatbot assistant. I'm expecting a small task like OCR, and you can show, for example, you have fine-tuned some results and evaluating the results So it's the evaluations and the fine tuning that we are expecting from the project. Okay. So for week 5, there are some code samples, fine tuning and evaluation. So if you run the code successfully and it should already done half of the project work. So the other half, which is to report the results and make some changes. If I remember correctly, the fine-tuning steps of the lab is only around 10. And you might, in your project, you can simply increase the number of steps of fine-tuning to see if it achieved a better result. Okay, so just pick a week and download the code and try to run it in the server first. And you will find if you do not have any idea or if you are struggling with coming up with a project title, please feel free to just use one of the code examples in the course. If you have other ideas, please feel free to train your own personalized language model or personalized AI or image recognition or text generation or speech generation or even song generation or in some cases video generation. But given the limited VRAM that we provide, say 16 gigabytes of VRAM, training a larger model might require more advanced skills. And of course, if you can use those advanced skills, it is very good. But to get good marks, I think you just need to modify the code and give your reasoning. Okay, so does that answer your question? No. Or yes? Oh, okay. So any questions regarding the project? If no, I think we should carry on. Okay, so let me okay. Let me close this and close this one. And I think so welcome back. Let me click the link. So um so in the previous sections, we treated the visual encoder as a black box, and we treated the visual encoder as a black box. Is this the right path? Okay. And pixel in, pixel out. Now we're going to crack open the box. We are going to look at the engine inside this SIGLib. So first, we have to ask why we are here. For the last 3 years, undisputed, the King version encoders has been the clip. So contrastive language image pre-training from OpenAI. It powers the Dell, and it powers Stable Diffusion, and it powers Lava, an open source model. So why did Google choose to ignore the industry standards and build something new? And why does Polygamma use a cyclic instead of clip? The simple answer to that is one mathematical function called softmax. So let's kind of refresh your memory of how clip works. It's used a contrastive loss. And say your batch size is n, and Clips tries to match every image to its correct text. To do this, it calculates a similar score for every possible pair in the batch. So if you have n images and n text, you have n times n matrix of similarity. Now here is the catch. Clip use softmax to normalize. It says for this specific image, out of dispatched, which one is the most likely match relative to the others. So operatively, this means the probability of a match depends on other items in the batch. So if I show you a picture of a golden retriever and the batch contain the text dog, Clip increase the probability of the dog. But if the batch also contains the text puppy, the Clip has to decrease the probability of dog because softmax forces all probabilities to sum to 1. So this creates a massive dependency. So every sample in your batch, okay, so every sample in your batch talks to every other sample. This leads to two huge problems. A small batch sample problem. If your batch is small, say 32 images, softmax does not work well. There aren't enough negatives to learn from. If the large batch problem is that if your batch is massive, say 64K images, the computation of n times n matrix becomes expensive and fairly complex. So Google realized this softmax bottleneck was holding them back, and they want to scale up, but Clip is the Clip's math was in the way, so you have to use something different. So the sigmoid solution independency. So now we have the cyclip. Full name of cyclip is actually sigmoid loss language image pre-training. So they simply replaced softmax with sigmoid, and that is the change. But let's look at why this changes everything. So with sigmoid loss, we stopped asking the question which text is the best match relative to the others. Instead, we ask a simple binary classification of the questions for every single pair. So do these two go together? Yes or no? Okay. So let's trace its implication. So this makes the comparison independence. So whether an image A matches the text A is calculated completely independent of text too. And scalability because there is no soft max normalization across the whole batch. You don't need to keep the entire batch memory on the chip to calculate the loss. You can split the batch across thousands of GPU chips and calculate the loss locally and just sum them up. So the clip complexity is much higher than the sigmoid So small batch performance, cyclib works great even with small batch because it doesn't rely on mining the negatives samples from the batch itself in the same way. So what does this mean for Polygamma? It means Google can train the vision encoder on massive amounts of data with much higher efficiency. So didn't they didn't need the massive um, three 32K or 64K batch size that clips required to be stable. They and also they could train faster and cheaper and get the model understand the world in a better way. Okay. Cyclip in general is a vision transformer with 27 layers. Although we keep saying the encoder processed the batch, but what does the 27 layers of processing exactly means? Okay, so let me give you the conceptual pictures. So for every transformer vision or text, there is a concept called residual stream. So imagine each token as carrying a small notebook. At every layer, the layer adds nodes to the notebook, and it never erased the previous nodes. By layer 27, every patches of the notebook contains cumulative record of all observed across all 27 layers. So this residue connections is simply the x in plus a function of x in equals out. So this f cannot actually remove any information from x in. You see this in early stages of the convolutional neural network as well. So the original patch representation x in flows through unchanged, and the other layers contribution f function of f x in is added on top. That's why a very deep transformer can be trained without vanishing gradient, and the original signal always flow through. Okay. Okay. The early layers behave like traditional computer vision filters, and each patch attends mostly to its immediate neighbor. So what do they detect? It detects edge, color gradients, and local textures. So if you visualize the tension maps at, say, layer 3, you will see each patch primarily attend to its 2 to 3 nearest neighbor. It is like asking what immediately around me. And if you think back to week 4, you ran the visual transformer patch visualizing a notebook on HPC, the heat maps that you saw, those patches those image patches light up were the early layer of attention which made visible. So the middle layer where the object emerged. Attention patterns become more global. It's almost similar to deep CNN networks. And a patch in the middle of a cat face begins to attend to patches at the ears and eyes and all other features. So semantically concepts is more like this cluster of high contrast patches with specific texture pattern is part of text. And again, the key mechanism here is multi-head attention. The model runs 16 attention heads in parallel, and each head is free to learn different types of relationships. One head might be specialized in tracking color co-occurrence, and the other head might specialized in detecting edge continuity, and so on and so on. So by layer 18, the patch's representation has been enriched with both its own local content as well as global context about what kind of object or region belongs to. And the final layer performed the highest level processing. So rationalized and the C-level understanding. So patches are no longer just cat, they become the cat that is above the table or text that appears inside the red box. So attention becomes highly selective, and key patches attracts stronger attention from faraway patches. So this is why Cyclips, despite never seeing pixel coordinate during this phase, implicitly learns a spatial relationship, say left, right, above, below, inside and outside. So by the output of layer 27, each of the 256 patch vectors has been transformed from the raw texture information into a rich 1152 dimension symmetric describer that encodes local texture, local identity, and scene level context. Okay, so let's talk about what does the SOL 400 M means. If you look at the model card in Hugging Face, it says Sigma SOL 400M. So we have introduced what is sigma. It just means sigmoid. The 400M means 4 million parameters. But what is SO? It is actually stand for shape optimized. It comes from another paper by the same team getting visual transformer in shape, scaling laws for compute optimal model design. So standard vision transformer like VIT base, VIT large, VIT huge were designed based on kind of a gut feeling or borrowing from numbers of birds. So they do not actually optimize the structure. There are various attempts to kind of find the optimal structure, and there is a branch called neural architecture optimization. However, it tries to find neural architectures more broadly instead of focusing on the standard transformer. So for example, Vision Transformer Large has 24 layers and a width of 1024. The researcher asked, is this actually the best shape? If we have a budget of compute, can we make the model deeper or wider, or should we increase the multi-layer perceptron size? And the result was they ran systematic experiments to find the compute optimal shape for a transformer. And they find that standard vision transformers were often too deep and too narrow. So the Seoul 400M architecture is the result of this optimization. It is approximately 400 million parameters, often round to 428 millions in some references. And it sits right between visual transformer large with 300 million and vision transformer huge, which have 600 million parameters. But it performs significantly better than large because its dimension, depth, width had mathematically tuned for maximum learning per flop. So this is why Polygamma feels so dense in its knowledge, and the vision encoder isn't just big, it is efficient, and every parameter is pulling its weight. Okay. Okay, so as you might already know, a model is only as good as its data. So CLIP was tuned on web image tags with 400 million pairs, and SIGLIP was trained on WebLE, sorry. WebLE is a massive with 10 billion images and 12 billion tags from the image text pairs across 109 plus languages scraped from the open web. As you might know, web data is kind of like garbage. Captions are wrong. Images are watermarked. So SIGLIP's signal loss are proved to be incredibly robust to this noise because it treats every pair as independent, yes and no questions. A bad pair, an image of cat with text, image 001 image, just act as a slightly bit of noise that averages out. So it does not skew the probability distribution for good pairs as badly as softmax does. So this massive, noisily multilingual pre-trained is what gives Polygamma the knowledge of the world. So, let's get some technical about the input. So SIGLIP patch, as already mentioned, uses a patch size of 14 times 14. Most vision language transformer use 16 by 16s. Again, it is fine-tuned, and you can refer to these in your project and try to change the size if you want. Okay, so before we conclude, we should ask, do we need this component at all? There is a competing architecture called the full Yole or a polygamma decoder only from a paper. This model just say drop the image, just chop the image into patch, project linearly, and feed them directly to uh, uh, the language model, and you can forget about the vision encoder. And Google tested it, and they removed the siglip and fed the raw the raw RGB patches into Gamma, and the performance dropped significantly. While simple, the decoder only approached struggled to extract deep visual features. The siglip encoder acts as the visual preprocessor. So it kind of digests the raw pixel and extract the semantic meaning, so shape, texture, and object, before the language model ever sees them. So this allows the language model to focus on reasoning rather than trying to figure out if a blob of pixel is cat or dog. Okay. So there is a website that I've made comparing the clip against the siglip. So it's kind of demonstrate it visually, but if you already know what clip is fairly basic. So we've mentioned about the similarity matrix. So we have the image tokens on the left and text tokens on the top, and we compare the matrix. So these are the matches pair. So the objective function of clip is to, with this batch, is to maximize the similarity and minimize all this loss. Okay. But as we have mentioned, this causes the problem of if you put, say, a puppy in here and a dog in here, and the image is actually a dog, and this will affect the learning, because you try to pull away the bond between an image of a dog versus a puppy, which what you actually should do is put them as close as possible. Okay, so you can play around with the mathematical function, and okay, so and you will see why the more if you play around with the probability of this function, you see why this sigma function is much better. Okay, so you can read more about this at home. I won't spend too much time on the mathematical part of the loss function. Okay, so before we look at the projector, I want to see if you have any questions. So if you have no questions, um, um, I'll carry on, and perhaps you might have already noticed in this course we have talked about so much about one operation. This is the matrix multiplication, because every model that we will be introduced in this course uses matrix multiplication. And of course, the most important part of transformer is also matrix multiplication. So, so when you talk about AI, you cannot you cannot kind of skip matrix multiplication if you want to do AI. So I highly encourage you to play around with matrix multiplication and in your spare time. So, but of course, you can get away with matrix multiplication if you want to kind of manage AI system or get some different types of jobs, like managing different agency, like in the first semester. So you can build a chatbot system without knowing any um, matrix multiplication, but I just want to stress that if you want to improve AI, I think this is this one single operation that you might want to know very well. Okay. So if you know matrix multiplication, the component to become fairly straightforward. It's just a projector. So it is kind of another word for simple matrix multiplication. So the second component is simply a matrix multiplication, changing the dimension of the vision encoder. So it uses a single linear layer and to project the 1,152 dimensions into this 2,048 dimension output vectors. And it just directly output the vector without the activation function. Okay. So it acts as a connectivity between the two models. And this is almost disappointing in its simplicity. So the projector in Polygamma is just, again, matrix multiplication. The input, so it kind of increase the vector size of the this slick lip encoder. And it takes the visual concept of cat and linearly rotates and stretches it until it becomes the concept of a cat in the Gamma language. So one additional detail worth noting is the projector is zero initialized at the start of training. This ensures that at the beginning of the joint pre-training, the visual and